Hello, A-level chemists. How are we? It is a miserable day here for April. I mean, this time last week I was wearing my shorts, but hey, it's absolutely freezing now and I hate it. We are here today to talk buffers. Okay, so buffers and oh, excuse, that's me in the background being a numpty. Okay, so we're here today to talk about buffers and electrochemistry. Okay, so buffers and electrochemistry probably two of the trickiest topics in A-level chemistry, both in physical, obviously. But essentially, there are some tips and tricks I can show you to help kind of ease your pain. With the buffers, it's about calculations, okay? Every year, every exam board, there's a calculation on buffers, okay? And they're all different, or are they? Okay, I'm going to show you how to hack these buffer questions basically by looking at what type of buffer question you have. There are only 3 types of buffer question you are going to get, and I'm going to show you what those types are and how to deal with them. Secondly, with electrochemistry, it's just so easy to get confused as to what's going on. So I'm going to show you a few kind of like memory hooks that can help you basically just sort the wheat from the chaff, get organized in your brain, exactly what's going on in an electrochemical cell and how to apply that in questions, okay? So there's a couple of things I'm going to show you. Like I said, first of all, buffers, then electrochemistry. So let's just remind ourselves actually of what a buffer is first and foremost, all right? So let's just share the screen here. So it's in the pH section, okay, or acids and bases section of your specification. So we need to know obviously what an acid is and what a weak acid is, and of course what a base and what the salt of a weak acid is as well. So a buffer is something that maintains an approximate pH. Now, whenever we think pH, we need to think hydrogen ion concentration. That's what pH is, okay? So one first tip is if they ask you to calculate the pH of something, just think hydrogen ion concentration. That's what you're aiming to find first and foremost. And then, of course, you can use minus log of the hydrogen ion concentration to find the pH. A buffer maintains a pH, therefore it must be maintaining a certain concentration of hydrogen ions, all right? So that's what we want to think. We're maintaining that concentration of hydrogen ions, even though like some small amount of acid or small amount of alkali may be added to the solution, it maintains that. The second thing is what a buffer is. So a buffer, let's remind ourselves, is a weak acid and the salt of that weak acid. It is a solution that contains both of those things. Those are your raw ingredients, if you like, of a buffer. Now, what gets set up is this equilibrium here. I'm just using the book here, okay, which you can find on the Chemistry Coach website, free to access for everybody. This is your setup, okay? Now, everything in terms of buffers is basically rooted in Le Chatelier's principle, all right? So what we've got is we've got our weak acid. I'm using ethanoic acid as an example here. And the negative ion here, that represents the salt of your weak acid. So if you imagine maybe sodium ethanoate that we've got here as a salt, but we're just basically looking at the conjugate base, I suppose you could call it, or the negative ion from the acid, okay? So this is our salt, and this is our weak acid, okay? Now, if an acid is added, okay, we need to think in terms of hydrogen ions. If we add an acid, we are increasing the concentration of hydrogen ions. Now, what happens in terms of Le Chatelier if we increase the concentration on one side? It moves to oppose the change. So what the buffer will do is use this salt and combine it with hydrogen ions and shift the equilibrium to the left to make more weak acid. And in doing so, bringing that hydrogen ion concentration back down. Okay, so it's always useful to think about this in terms of hydrogen ion concentration. Now, what happens if you add an alkali? Okay, well, an alkali is going to decrease our hydrogen ion concentration. If we add that in, it's going to neutralize the hydrogen ions that are in solution. So what does the equilibrium do? Le Chatelier states that if this concentration comes down, more of this will dissociate, shift the equilibrium to the right, and therefore bring that hydrogen ion concentration back up to a normal level, and obviously as a consequence produce more of these anions, produce more of the salt technically, okay? So whichever you do, add a small amount of acid or small amount of alkali, then that's going to affect the position of the equilibrium. So always, always, always think in terms of hydrogen ions. Acids donate hydrogen ions. So that's going to shift the equilibrium to the left to bring that hydrogen ion concentration back down. Alkalis reduce the hydrogen ion concentration by neutralization. So as we just shown here, that's going to shift the equilibrium to the right. So everything in buffers is related back to Le Chatelier's principle. So make sure you're up on that. So what sort of questions can it ask us in terms of buffer calculations? Okay. Well, let's have a look at our expression first and foremost. Now, this is a simplified version of what we've just been looked at. This is your acid, okay? You've probably seen this before, HA. The H here is, of course, the hydrogen ion that dissociates from that weak acid. I should say at this juncture, actually, we have to use a weak acid because they are weak acids, because they only partially dissociate in solution. They exist in equilibrium. We can't use a strong acid because it all just fully dissociates. There's no equilibrium set up. So that's why it has to be a weak acid. Now, in order to find, excuse me, I know why I've done that. In order to find, like say, for example, the pH of a buffer, it's only acid buffers we'll ever work with, all right? Only ever acid buffers that we work with. So we know our Ka expression, and we should know our Ka expression. Now, one other thing I'll point out here, that when you're calculating the concentration or the pH of a weak acid, you can use this, okay? So you can use H plus concentration squared over HA for weak acid calculations, okay? And that's because when a weak acid dissociates, we can assume that the hydrogen ion concentration and the anion concentration are the same. So that's why we're using H plus squared, because they have to be the same as each other. Not true in a buffer, because what we've done is we've added a weak acid and artificially added more of these anions by adding the salt. So no longer are these two things the same. So we cannot use this expression over here when it comes to buffers, because H plus and A minus are not the same concentration. They might be in a random kind of question, but they're not, okay, because we've artificially added the salt, okay? So as I've said here, we can't use that. So in terms of rearrangements, we should be able to rearrange the Ka expression given the Ka of the weak acid. If we want to find the acid concentration, we've got our rearrangement, our hydrogen ion concentration, and therefore our pH, then this is the most common expression we'll be asked to use based on the fact that most questions ask us to find the pH of something. But of course, if we want the salt concentration, then this is our rearrangement here. Now, questions. There are 3 types of buffer question that you're going to come across, okay? And I'll list these. So number 1, they could ask you to find most of the time the pH. Let's be honest. Most of the time it is the pH. But, you know, they could ask you to find anything really. But the main point here is that there are 3 different types, or I say flavors, if you like, of buffer calculation, okay? And it depends on the information that you're given and how to actually attack it. So, number 1 here is a question where they're asking you to find the pH, or maybe the mass of salt added, or maybe the concentration of acid. You know, the things they can ask you is different. But the crux of the question is this, that basically they are adding a weak acid and the salt of the weak acid to a solution, okay? So basically they're putting in the raw ingredients of a buffer into a solution, and maybe they'll ask you to find the pH, or maybe they'll tell you the pH and say, okay, well, what mass of salt do we need to put in order to make this solution? But the crux of the question, the baseline of the question is that they're just mixing the raw ingredients of a buffer together. That's the weak acid and the salt of the weak acid. So for example, propanoic acid and potassium propanoate. All right, so, you know, any combination of those, but just spot the weak acid and the salt that you're mixing together. So that's really where we're creating a buffer using the raw ingredients. There is a second method, however, of creating a buffer, and that's where we take a weak acid and react, very importantly, with a strong base. Okay, so we are creating a buffer, but this time we're using these two ingredients instead of this one. Okay, now what's really important here is that a weak acid, or the weak acid in this situation, has to be in excess. Okay, it has to be in excess. So let me just show you real quick what I mean. So let's say we react ethanoic acid and sodium hydroxide. Okay, now what that's going to make is sodium ethanoate, so that's our salt, and it's going to make water. Now, as these two react together in a 1-to-1 ratio, what's going to happen is, let's say, I'm just going to use easy numbers here. Let's say we got 10 moles of the acid and we've got 6 moles of our sodium hydroxide. Okay, now again, notice the acid has to be in excess. Well, we haven't got any of these to start with, but obviously once the reaction's happened, we're going to end up with, because this is a 1-to-1 relationship, all of these NaOH, all of the NaOH is going to get used up in the reaction. And because it's 1-to-1, we're going to end up with 4 moles of the weak acid left over, but we're going to create 6 moles of our sodium ethanoate, our salt, okay? And yeah, we're going to make 6 moles of water as well, but we're not bothered by those. So what you'll notice is that by this reaction, in this way of creating a buffer, this is essentially leaving us with a solution of weak acid. We've got 4 moles of it, and the salt of the weak acid. So that's why it's important, and in every question you will see this, that the weak acid is in excess when compared with the strong base like the sodium hydroxide. Because otherwise, if the sodium hydroxide's in excess, then you're not going to have any weak acid left over, and you're not going to create a buffer solution. All right. So what you're aiming to do here, or what the question is aiming to do, is create a buffer by reaction of a weak acid and a strong base. And what you end up with is whatever's left over of your weak acid plus whatever you've produced in terms of a salt. And that is another question type that we can get. So these two together, the type 1 and type 2, okay, these are where we create a buffer. Okay, so that's question types 1 and 2, where we're creating a buffer, and you need to be able to spot those. All right. Now the third and final type, okay, this is where we have an existing buffer to which we've added either a strong acid or a strong base. Okay. So this is a question whereby you're not creating a buffer, okay, and they're not going to ask you questions on how it's created or what the final pH of the buffer solution produced is concerned. They've given you information about an existing buffer and what happens, or how does the change in pH, how is the pH affected, if you like, if we add a small amount of strong acid or a small amount of strong base. Well, this is where what we just talked about, HA, being dissociated in an equilibrium to this, okay? Now let's say we start with, and again I'm using easy numbers, 10 moles of our acid, and we know that we've got, I don't know, just 10 moles of our A minus, okay? Now let's say we add, I'm going to do these in different colors, let's use green, okay? No, let's not use green, let's use acid and base. So let's say I add an acid in red, okay, that makes sense. So if I add, I don't know, 0.5 moles of an acid to this, okay? Now what's going to happen in terms of our equilibrium? Well, when we add an acid, okay, we add basically 0.5 moles of H+. Let's say it's HCl we've added, okay? So what's going to happen here is our hydrogen ion, number of moles of hydrogen ions is going to increase by 0.5 moles. And of course, a buffer solution will oppose that change. So what's going to happen? Well, the equilibrium is going to shift to the left. To do so, it's going to have to use 0.5 moles of our A minus. It's going to have to use the same number of moles of your salt in order to shift that equilibrium to the right and bring that hydrogen ion concentration back down. So what we see as a consequence is that once the equilibrium has shifted, after we've added our small amount of acid, the amount of moles of our acid now is 10.5 moles, okay, because it's shifted to the left, okay. And what's happened here is the A minus, the salt, has now become 9.5 moles, okay. So when you add an acid, basically HA concentration increases and your A minus concentration decreases, okay? Because we've added an acid, the equilibrium reacts to that, Le Chatelier's kicks in, and it shifts to the left. So your HA is going to go up by the same amount of moles of acid that you've added, and your A minus is going to go down by that because it gets used to reassociate with the hydrogen ions to produce the HA. Now, of course, I'm pretty sure you're going to be ahead of me here, but when it comes to a base, okay, so if we add 0.5 moles of NaOH, let's say, our hydrogen ion concentration is going to go down by 0.5 moles. Now, of course, Le Chatelier's is going to oppose that. It's going to want to bring it back up. So what actually happens here is that the acid concentration goes down, because to replace those hydrogen ions that have been neutralized by the strong base, that's then going to have to replace those hydrogen ions. So this HA now becomes 9.5 moles, okay, and our A minus becomes 10.5 moles, okay. So the opposite is true here for where we've added a strong base compared to a strong acid. Okay, so it's about shifting the equilibrium, and it will shift ever so slightly, but what happens is it maintains the pH. Okay, it maintains the pH, not perfectly, but you know, it does a really good job of resisting any change in pH when we add a strong acid or a strong base. So here are our three types of buffer calculation. Okay, they're the only three types you're going to come across. Now, what I've done is I have put together, let's call it almost every single buffer calculation from the major exam boards. Okay, so that there, my friends, is a document that has every single buffer calculation question in and all the answers as well. Okay, because it doesn't matter what exam board you are, a buffer calc is a buffer calc. It's a buffer calc. All right, so let's have a look at it. Let's have a look at this. So let's see if we can identify what type of question we've got, and then we know how to deal with each of them. Okay, so let me bring this up actually. So I've got this here. Okay, so in the bottom, where is it? Well, just on the left hand side here. Okay, or should we put it bottom right? Let's put it bottom left. Okay, down here. So there are three types, okay, in the bottom left-hand corner, like down there. So we got type 1 is a weak acid plus the salt of a weak acid, where we're creating a buffer. We got type 2, where we're also creating a buffer, but this time using a weak acid and a strong base. And we got type 3, where we're basically just tweaking an existing buffer by adding a small amount of acid or small amount of base. So let's have a look and see if we can identify what type of question is what. So these are in no order whatsoever, ladies and gentlemen. All we want to know is what type of question we're dealing with, and then of course we know how to deal with them after. So a buffer solution is made, right, well first of all I know it's type 1 or type 2 by adding 6 moles or 0.6 to the minus 2 moles of sodium hydroxide to a solution containing this many moles of ethane dioic acid. Okay, and they've given us the reaction there. So this is type 2. The reason it's type 2 and we know how to deal with it is because we got our strong base here and we got our weak acid here. So this is a type 2 calculation. On to the next. So this one here. So a buffer solution with a pH of 3.87 was prepared using ethanoic acid. So we got a weak acid and sodium ethanoate. So anybody that's watching in the chat, if you want to tell me whether it's type 1, type 2 or type 3, you can put that in the chat for me. I'll give you a few seconds to do so. So it's again, looking at the question, looking at what it's asking you, how the question's set up, and then you can say exactly what type it is, okay? So this is again where we're creating a buffer. So it's type 1 or type 2. We're using ethanoic acid and sodium ethanoate. Well, that's a salt. So this is type 2. Okay, this is type 2, this one. Okay, sorry, type 1, my apologies. Type 1. I got confused with my types there. So yes, it is type 1. Thank you very much, Alice. All right, so yeah, It's ethanoic acid and sodium ethanoate. Next one, okay, a different buffer solution. The concentration of ethanoic acid and the concentration of ethanoate ions was this, and then a 7 times 10 to the minus 3 sample of sodium hydroxide was added to this buffer solution. So what's this? Is it type 1, type 2, or type 3? For 6 marks here, okay, we've got an existing buffer solution. We're adding some sodium hydroxide to it. So what type have we got? Type 1, type 2, or type 3? Type 3 again, Alice. Thank you very much. Very much appreciated. Okay, so we've got type 1, type 2. Let's have a look at a couple more, just for giggles. A buffer solution contains sodium ethanoate and ethanoic acid. A sample of 5 centimeter cubed of 2 molar HCl was added to this buffer. Calculate the pH of the solution form. So type 1, type 2, or type 3. Let's keep this train rolling. Type 1, type 2, or type 3. Three again. We're on a roll. Next one. A student prepared a buffer solution by mixing this many moles of salt, Kx, to this volume and concentration of a weak acid mixed thoroughly. The student then added 3 times 10 to the minus 4 moles of potassium hydroxide to the buffer solution. Type 1, type 2, type 3. Alice, you're on a roll. Don't let me down. Type 3 again. Absolutely. So you see, like, you know, these first ones, they're mostly type 3. Let's just have a look. I mean, these are all AQA questions. Let's go here. Okay. Let's go. Where are we? There we go. Let's have a look at this one. Okay, so nitrous acid is a Bronsted-Lowry acid with a pKa value of 3.34, blah, 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 blah. Okay. So a chemist adds, where are we? 100 centimeter cubed of sodium hydroxide to 100 centimeter cubed of HNO2, which is our acid, our weak acid, okay? So they've added NaOH to a weak acid, and they made the solution up to a decimeter cubed. So type 1, type 2, or type 3. There's lots of other stuff going on here, but at the base of it, it's what type? Type 1, type 2, or type 3? Type 2, absolutely. Okay, let's do one more. Let's just pick one from EdXL. Let's go crazy. Here we go. So a buffer solution was made 20 centimeter cubed of butanoic acid of this concentration and 30 centimeter cubed of sodium butanoate. Calculate the pH of the buffer. Type 1, type 2, or type 3? It is indeed type 1. So we know we can identify these, okay? We just need to know how to deal with them, okay? So let's just do this one. We'll work through one of each type, okay? So a buffer solution was made of 20 centimeter cubed of butanoic acid of a concentration of 1 mole per decimeter cubed and 30 centimeter of sodium butanoate of this, okay? And we've got our Ka. So what we want to do is just be careful here, okay? The volume, the total volume of our buffer solution is 50 centimeters cubed. Okay, we need to bear that in mind. So just be careful when you're making buffers, watch the volume. Okay, sometimes they add maybe a solid salt to a weak acid solution, in which case the volume is not going to change. But here they're using two volumes, one of the weak acid, one of the salt, okay, both in solution. So we're going to have a new total volume, which we need to take into account. So the first thing I'm going to do is number of moles of the weak acid, the butanoic acid. So that's conc times vol. So that is 20 over 1,000 times 0.1. And that is 2 times 10 to the minus 3 moles of our weak acid. And the number of moles of salt, again, conc times vol. And that is, that'll be, conc times vol. So it's 30 over 1,000 times by 0.305, and that is 9.15 times 10 to the minus 3 moles. Okay, so those are our numbers of moles. What we need to do now is find their new concentrations once we've mixed them together in terms of 50 centimeters cubed. So the new weak acid concentration is number of moles divided by volume. So that's 50 centimeters cubed. So 2 times 10 to the minus 3 divided by 0.05, because that's 50 centimeter cubed in decimeters. And of course, the new concentration of the salt, number of moles divided by volume, so that is 9.15 times 10 to the minus 3 divided by 0.05. And I've got that in my calculator, so I'm going to do that first. So that is 0.183 moles per decimeter cubed, and then 2 times 10 to the minus 3 divided by 0.05, and that is 0.04. Okay, now we've got our new concentrations of weak acid and salt. So we know that Ka equals H plus A minus over HA. Well, we know Ka, we know A minus because that's our salt, we know HA because that's there. So all we need to do, of course, is rearrange to find H plus. So that is Ka times HA over A minus. So that is 1.52 times 10 to the minus 5 times 0.04 all over, what was it? 0.183, which is our A minus. So that gives us our hydrogen ion concentration. So that is 1.52 times 10 to the minus 5 times 0.04 divided by 0.183. And that gives us, there we go, 3.322 times 10 to the minus 6. And therefore, pH equals the minus log of that answer. So minus log answer. And that gives us a pH of 5.48. Okay. So even though it's kind of like the simplest type, you know, just mixing the raw ingredients together, you know, this bit here was all about finding the new concentrations. I went through that from first principles. There's probably a way, you know, of going from, you know, you could probably multiply this concentration or divide it by, well, what is it, 2.5 or something like that. But, you know, I'm a big fan of doing things from first principles here. Okay, so that's how we deal with type 1. Let's have a look at a type 2. I'm sure we came across a type 2. There was one there. Let's not do that one because it looks a bit more involved. That's a type 3. That's a type 3. That's a type 1. That was a type 2, was it? Yeah, okay. That was a type 2. Or should we do a different one? That's a 3. That's a 3. Here we go. There we go. This is a type 2. This is a nice straightforward one because, you know, obviously I just want to show you the basis of how to do this. So buffer is made by adding 2 grams of sodium hydroxide to 500 centimeter cubed of 1 molar ethanoic acid solution. So this is a really good example of what I mentioned before, in that they're adding a solid to a solution. So we're assuming that there's no change in volume, okay? So we need to calculate the pH of this buffer. So we know that ethanoic acid, so CH3COOH, reacts with our sodium hydroxide 1-to-1, and it'll always be a 1-to-1. I've never seen anything different, okay? So this is our salt that we're making, and obviously the water that we're making as well, and we can basically just ignore that, okay? So firstly, we need the numbers of moles. It's all about numbers of moles here. So the number of moles of ethanoic acid is conc times vol. So its concentration is 1 divided by volume, which is basically 0.5. So that is 2 moles of that. Now the number of moles of sodium hydroxide, well, that's mass divided by molar mass. So sodium hydroxide, what's that? That's 23 plus 16, which is 33, 39, which is 40. Okay, 2 divided by 40, nice number, and that's 0.05 moles. Okay, so we know the number of moles of both of these. Now what's going to happen when these two things react together? Notice again how our weak acid is in excess. Okay, is in excess. We've got more acid than we have sodium hydroxide. We haven't got any of this to start with, but after the reaction, this is going to go down by 0.05, so that's going to be 1.95, okay, moles of ethanoic acid. This is going to be 0, but this is going to be 0.05, okay, because these two have reacted together. This is the limiting reagent, so that's why we've made 0.05 moles of our salt, okay? So now what we need to do is find the new concentration, I should say, new concentration of acid equals number of moles divided by volume, so 1.95 divided by 0.5, and that equals 3.9 mole per decimeter cubed. Oops, excuse my rubbish writing there. And the new concentration of salt, well, the concentration of salt, again, is number of moles divided by volume, so 0.05 divided by 0.5, and that is 0.1 mole per decimeter cubed. Okay. Now, once again, they've given us the Ka, and once again, they're asking us to find the pH. So we know that H plus concentration equals Ka, what was it? Ka, H plus, A minus, so that goes underneath. So Ka times Ha over A minus. So that is 1.74 times 10 to the minus 5 times acid, which is 3.9, over that, which is 0.1. So 1.74 times 10 to the minus 5 times 3.9 divided by 0.1. And that is 6.786 times 10 to the minus 4. And then we're on the home stretch that pH, okay, is the minus log of that. So let's just do that. And that is 3.17. Okay, so that's how we go about type 2. Okay, and like I said, it's about spotting the baseline of the calculation. Okay, is it type 1, type 2, type 3? They could ask you, very easily, and I'm sure I saw one before, where they might ask you, like, what mass of sodium hydroxide do you need in order to create a pH of 3.17? So, of course, it's still the same type of question, but it's just a different rearrangement of it. Okay, so a different way of going about it. That's all it is. Now, let's have a go at a type 3. Let's have a look at the very first one we looked at because, there we go, this one here. So in a buffer solution, the concentration of ethanoic acid was 0.26 and the concentration of ethanoate ions was 121. A 7 times 10 to the minus 3 mole sample of sodium hydroxide was added to 500 centimeter cubes of this buffer solution. Okay, we need to calculate the pH. So we need to set up for type 3. The first thing to do is set up, we've got ethanoic acid, and that dissociates into, basically, let's call that our salt, and H plus. Okay. Now, the first thing we need to do, we've been given the concentrations of the ethanoic acid and the ethanoate ions. Okay. And we know we're dealing with this volume of this current buffer solution. So what we need to do is find the starting numbers of moles of our weak acid and our ethanoate ions. Okay, so obviously number of moles equals concentration times volume. So we're going 0.26 for our acid times 0.5 because it's 500 centimeters cubed. And that gives us 0.13 moles of our acid. And of course, we have got 0.121 times 0.5, and that gives us the starting numbers of moles of our salt, which is 0.0605. Okay, so those are our starting numbers of moles here. Now we're adding 7 times 10 to the minus 3 moles of sodium hydroxide. Okay, now remember what I said right at the beginning of this. If I add sodium hydroxide, it's going to react with or neutralize these hydrogen ions. So the equilibrium is going to shift to the right, okay, to replace those hydrogen ions. So what we know is that the sodium hydroxide reacts 1-to-1, and it will always be 1-to-1. They'll never do anything shady. It's always 1-to-1. So if 7 times 10 to the minus 3 moles of sodium hydroxide is added, this is going to go down by that same amount. Okay, so the new number of moles, this is minus 7 times 10 to the minus 3. So 0.13 minus 7 times 10 to the minus 3 equals 0. Let's move this down. 0.123 moles. And this is going to go up by 7 times 10 to the minus 3 because as it shifts to the right, yes, it's replacing the hydrogen ions, but we're making more of these as a consequence as well. You can't do one without the other. So 0.0605 plus 7 times 10 to the minus 3. And that is 0.0675. So these are our new numbers of moles of weak acid and our salt on our conjugate base, if you like, after we've added that sodium hydroxide. But of course, it's not numbers of moles. We needed to convert it into number of moles to do this. But now we need to find the new concentrations because in Ka, we need to use concentrations. So the new concentrations, okay, and obviously concentration is number of moles divided by volume. So I'm dividing each of these by 0.5 because that is our volume, okay? So I'm going to do the one on the right first because it's already in my calculator. So that equals 0.135 now, the concentration of the weak acid. Notice how it's gone up. Let me just clear the decks up here. Notice how it's gone up from this, okay? No, sorry. Yeah. No, what? That was the acid. No, duh, this one. So it has gone up from the original concentration, which makes sense. So that's just like a little bit of a common sense check there for you, as long as you don't mess it up like I did. 0.13 divided by 0.5, or 123, and that is 0.246. Okay, which of course has gone down from the original concentration of ethanoic acid because it's been used up a little bit. Okay, so we want to find the pH. So once again, H plus equals Ka times A minus all over HA. No, it's the other way around. HA over A minus. My apologies. That's right, isn't it? Yeah. So that is, they gave us the Ka somewhere else, didn't they? There it is. 1.74 times 10 to the minus 5. Multiplied by the new concentration of HA, which is 0.246, the acid, over a new concentration of our salt, 1.74 times 10 to the minus 5 times 0.246, divided by 0.135, and that equals 3.171 times 10 to the minus 5. And of course, pH is the minus log of that, as usual, and that is a 4.50. We're all friends here. Let's round that up. Okay. Right. So they are your three fundamental kind of three fundamental baseline kind of question types for buffers. All right. So two skills that you need to develop here. One is spot the type of question that you've got, type 1, type 2, or type 3. And second thing is know how to deal with each of those types. And I swear to you, right, there's a load of these in here. I mean, it just keeps going, all right? Just buffer question after buffer question. And that's because every single year, every single exam board puts one in, okay? And I don't think this is exhaustive. I think this goes up to 2022, something like that. So the 23, 24 papers are kind of free and easy for you, but it's got all the answers at the end there as well. So please feel free to use and abuse that and practice, practice, practice. Now, if you want to, obviously in the book, we've got, all the information you need there on buffers, exactly how basic buffers work as well. You'll have no calculations on those, why we get buffer regions in pH curves. And of course, there's a video there. If you're a Chemistry Coach member, you can access the worksheet and the video and everything like that, which is different to the one you're seeing. So how to smash buffer calculations. But in terms of acids and bases, shows you how to use pH curves to calculate Ka, all the different types of pH curve and how to use indicators and things. So like literally everything at your fingertips. You can access for free at the Chemistry Coach website. Share it with your friends. It's, like I said, it's absolutely free to access. But obviously, if you want to access the worksheets and the videos and the AI and everything like that, there's a little discount code kind of scrolling on the bottom down there, and it's just one payment. Okay, one payment, and you get access to like literally everything in there, including the videos, the worksheets, flashcards that I've written, not written by AI, not written by an algorithm, not kind of just full of questions, because it really annoys me when it's like, oh, here's some flashcard packs, and they're basically just questions. That's not what flashcards are for, okay? Either that or there's about 50 million of them, and it's just, you got no chance of actually being able to go through them all. So I've whittled everything down for each topic for your exam board, the fundamental facts that you need to remember. That's what flashcards are for recall. So things like Group 2, Group 7, your transition metals, the flashcards for those are unparalleled, all right? And they're all digital as well, so you can just scan the QR code, just use them on your phone as and when. There's quizzes in there as well, which I've written, okay? So multiple choice quizzes for every single section, and obviously question packs. They're bigger for the ones which are more skills-based, so calculation-based stuff, you're going to find more question pack questions, whereas the recall things like periodicity, Group 2, Group 7, transition metals, and organic chemistry, really, you're going to find more flashcards for that. So the resources are tailored to how best to revise each of those different topics. And on top of that, as I keep mentioning, the AI that I've built for your exam board it's the only one. It's unparalleled, okay? ChatGPT does not do the job for you, okay? Please, please, please do not use ChatGPT. It's dangerous, okay? Because it'll give you question types that aren't in your exam. It'll give you information that you don't need to know, maybe miss out information that you do need to know. So I've custom built this AI to be specific to your exam board, nothing more, nothing less. It will write questions for you, multiple choice, exam style question for calculations, talk you through the practicals. It'll teach you something from scratch if you want it to, and it's going to be linked. Not quite yet, but I'm working on linking it to the book as well. So if you want to see pictures and diagrams to support your learning, it's all kind of interconnected with the quizzes and the books and everything else like that. Okay, so yeah, check that out. And it's just one payment, and you got access until the end of the year. And I would try to make it affordable as well. Okay. Any questions on buffers before we move on? I thought that's going to take me half an hour, but it's taken me 42 minutes. So it's leaving us very little time to talk about electrochem. Any questions on acids, bases, buffers? Any advice I can give you right now? I'm more than happy to answer those questions for you before we move on. I'm going to give you kind of 10 seconds or so to kind of put that in. If not, we'll move on to electrochem while I have a little drink. Okay, take that as a note. Fantastic. Right. Well, let's check out electrochem, shall we? So electrochemistry, as I say, it can be a topic of misery, I think, for a lot of students, because the types of questions you get and just having it can be very confusing. It's really easy to lose your way in electrochemistry, okay? But if you just kind of slow things down while you're learning it, a lot of it just makes sense, okay? And I want to just run through a couple of things with you today, and I'm going to give you some questions on this. I'm going to give you a question pack like I did for buffers, but this is more about helping your understanding and giving you some linchpins to kind of hold on to whilst you're looking at exam questions, and hopefully kind of just give you a bit of clarity when it comes to answering these exam questions as well, okay? So let's go over to the book again, okay? So, bit of preamble here about redox, oil rig, oxidizing, reducing reagents. This is all from year 12, okay? So combining half equations, all these skills are super, super important from year 12 before you actually get going in electrochemistry in year 13, okay? So redox potentials, okay? It's about how powerful an oxidizing or reducing agent something is. You've already looked at this in year 12, okay? Hey, welcome back. So you've already looked at this in year 12, okay? So you know that quote from, let's say, even GCSE, group 1 metals get more reactive as they go down the group. When they react, they lose an electron. So what we're doing is they are being oxidized themselves. So metals are reducing agents. They give electrons to other things and reduce them, okay? So we know that the reducing power of metals increases as you go down the group because they lose an electron more easily. All linked again to, as we mentioned yesterday, atomic structure and how easily they lose an electron, so linking to first ionization energy. So redox power of metals increases as you go down group 1 and group 2, so the reducing power of them. Halogens, on the other hand, okay, they're oxidizing agents, okay, so they cause other things to lose electrons because they gain them themselves. But oxidizing power decreases down the group as far as halogens are concerned, okay, because iodine is not very good at attracting electrons because it's got loads of energy levels. So it all links in and makes sense. When you've got your halide ions, which are reducing agents, because they, like metals, can give up an electron. Okay, they've gained one, doesn't mean that they never lose it again. Iodide ions are the best at losing an electron. In other words, they're the best reducing agents of the halide because, again, it's got loads and loads of shielding, very weak attraction between the nucleus and outer electron, so it loses it dead easily. So it's a really good reducing agent, okay? Hi, Mohammed. Specify. Am I talking too quick? What's going on? So let's move on to electropotentials, okay? Let's have a look at our electropotential table here. Now, this annoys me as well. In exams, they don't always do this, but the standard method for measuring electrode potentials, it's all right. That was just a bit of preamble, Mohammed. I'm getting into the good stuff now, okay? And, you can go to the Chemistry Coach website and just kind of take a look at that for yourself as well, okay? So these are our electropotentials, okay? Now, everything we should know is measured against the concept is measured against the SHE, the standard hydrogen electrode, okay? That's okay, if people don't understand, they don't understand. That's everyone's different, okay? But you can rewind, okay? So everything's measured against this. If you put your hydrogen electrode with a hydrogen electrode, it's 0, 0. Okay, so there's no difference in redox potential. But we're talking here about all the other things compared to the standard hydrogen electrode. So the first thing I want to point out really here is that everything on this side of the equation is a reducing agent. Okay. Why? Because these things are oxidized themselves. Anything that's oxidized itself to form something else, okay, then it's a reducing agent. Now, what you've got to remember is when you see this and you got the most negative, okay, the most negative electropotential, that's where you're going to find your strongest reducing agent. Okay, this is A-level chemistry, Mohammed, A-level chemistry. So year 13, UK A-level chemistry. So lithium here, because it's the most negative in terms of the electropotential, that's our strongest reducing agent, okay? Not Li+, no. Lithium, okay? Because lithium gets oxidized to Li+. So lithium is the reducing agent. As I said before, metals are reducing agents, all right? So your strongest reducing agent is always found with the most negative. Now, that kind of links and kind of checks back to what we learned in year 12. And that is if an oxidation number decreases, goes down, it's been reduced. So we got a negative number. Our strongest reducing agent kind of links to that. Okay, so most negative, that's where we find our strongest reducing agent. And all of these are potential reducing agents depending on what you hook them up with. On the other side, on the flip side of things, all of these things down here, these are oxidizing agents. Oop, and I'll just get rid of this because we don't need that anymore. All of these are reducing agents, okay? Thank you very much, Mohammed. So the most positive half cell will contain the strongest oxidizing agent, okay? So most negative half cell, that will contain your strongest reducing agent. Most positive half cell, that contains your strongest oxidizing agent. Of course, all of these are oxidizing agents because they get reduced themselves to form the other species. All right, so you can always rely on that. It doesn't matter which way around this table runs, from most negative to most positive, or the other way around. You just think most negative, that's our strongest reducing agent. Most positive, there's our strongest, oxidizing agent. And of course, hydrogen sits in the middle. Now, linked to this, the other thing I want to show you here is that what actually happens when you hook two half cells up together, okay? So let's just pick two random ones. Let's go calcium and let's go copper, okay? So let's say I hook these two up in an electrochemical cell. So I put the two solutions next to each other, our two half cells, connect them with the high resistance voltmeter and our salt bridge, okay? What's going to happen? Well, you can rely on something called the anti-clockwise rule, okay? The anti-clockwise rule. If you put, let's say these are the two we're focusing on. If they ask you, what's going to happen in the electrochemical cell when these two things react together? Well, the anti-clockwise rule states that if you put the most negative one on top, which we've got, okay, minus 2.87 is more negative than plus 0.34, of course. What's going to happen is the calcium, the strongest reducing agent, is going to be oxidized to Ca2+. So it goes from right to left. The one underneath, the most positive one, goes from Cu2+ to Cu. It gets reduced itself. So our reducing agent reduces the Cu2+, and our oxidizing agent oxidizes the Ca. Okay, so this is the anti-clockwise rule. So if you put one on top of the other, like so, okay, you're going to get your arrow round to the left and this one round to the right. So you can see it's moving in an anti-clockwise direction. All right. So if you're ever struggling, okay, to think, okay, what's happening to this one and what's happening to that one, anti-clockwise rule can sort you out. And then from there, you can say that Ca is going to Ca2+ and 2 electrons, and the Cu2+ is going to Cu, plus 2 electrons is going to Cu. And what you can do is, once you've written those out in the direction that they're both traveling above and below each other, you can actually just cancel out the electrons and merge the two half equations together, boom. And that gives you your overall equation, okay? It gives you your overall equation. So Ca plus Cu2+ gives you Ca2+ and Cu, okay? So electrode potential is the, as I mentioned before, the redox power of that half cell compared to hydrogen, okay? So it's literally the reading you get on the voltmeter if you hook up any one of these half cells with the standard hydrogen electrode, okay? That's what electrode potential is. So the bigger the potential, okay, the stronger the redox power of that, the more it wants to kind of react. I think of electrode potential and voltage, it is a potential difference, but it's like the push or pull factor of the electrons looking to be transferred. Let's talk about that actually. So let's take this one. So we talked about copper. Copper's got a positive E0 value. Now, whenever you see these cells set up, okay, whenever you see these cells set up, if you've got a standard hydrogen electrode, it's always placed on the left. It's always placed on the left, okay? So what happens here is that if we hook this up with a Cu2+ electrode, what's going to happen is that the hydrogen is going to get oxidized and the copper is going to get reduced, okay? Let's have a look, just prove that, okay? So if we get rid of these. So anti-clockwise rule, we've got hydrogen and we've got copper. Hydrogen is going to get oxidized to H+, Cu2 is going to get reduced to Cu, okay? So what's happening here is that because oxidation is happening in the in the standard hydrogen electrode, it's losing electrons, okay? So these electrons build up in the electrode, and they want to move from left to right across here and then provide electrons to here for the reduction. Okay, but what's actually happening is this high resistance voltmeter here does not let any electrons past. So these reactions aren't really happening. All this voltmeter is doing is kind of measuring the push and pull from each side and will give you a reading. It's the potential difference on either side. That's the other name for voltage, of course, isn't it? So the electrons are looking to move from left to right. And as they move from left to right, that's why we get a positive value. The E0 cell here is a positive value, okay, plus 0.34. So that's why it's a positive value for copper, okay, because the electrons are looking to move from left to right because the shear is being oxidized and the copper side is being reduced. On the flip side of things, if we're looking at magnesium, magnesium's actually got a negative voltage. Now the reason for that, if we go back again, oops, no, don't want that, undo. If we go back, we can see compared to the hydrogen electrode, magnesium's got a negative electrode potential. And that's because when we hook up magnesium to the standard hydrogen electrode, look what happens. The electrons, oxidation's happening here. Okay, the electrons build up, they look to move from right to left, basically going the wrong way through the voltmeter, which is why we've got a negative value on our reading, okay, because it's the metal that's this time being oxidized and the She, the standard hydrogen electrode, being reduced. So that's why we end up with positive and negative values when it comes to hooking up our other half cells to the standard hydrogen electrode. It depends. Are they stronger oxidizing agents or stronger reducing agents than the standard hydrogen electrode? That dictates which way the electrons move and therefore what sign you're going to get on your voltmeter. So not every question you get is based on half cells being hooked up to standard hydrogen electrodes. A lot of the time, most of the time, they're looking at combining, like we did before, copper and calcium, I don't know, potassium and zinc, or Fe and iodine, or I don't know, something like that. That's where it can get a bit confusing, okay? So here's what I want you to remember, all right? So if we look at this one, aluminium and copper, okay? We have no idea which way this is going to go, okay? But you can rely on the standard notation or the standard kind of principles applied to this electrochemistry here, okay? And I've kind of whittled it down to this. On the left, okay, so on the bottom down here, you'll see on the left, oxidation occurs, it's the anode and it's the negative electrode. So you can rely on lone. So whenever they give you two half cells hooked up to make a cell, you can rely, and certainly should be able to rely, on the fact that the one on the left is where oxidation is occurring. So in this case, aluminium is being oxidized to Al3+. It's the anode. Now the anode, because it's producing electrons, because it's being oxidized, it's the anode, okay, where all the electrons are building up. After all those Al atoms are having their electrons stripped away from them, they're all building up in the electrode there. And it's the negative electrode, which makes sense because it's full of electrons, all right? So left, oxidation, anode, negative. Remember lone. And of course, RRCP, yeah, it's not as nice, but it's literally just the opposite, okay? On the right, reduction occurs, it's the cathode, and therefore our positive electrode, okay? So what happens here is, because we always put the one that's oxidized on the left, you should always get our electrons are going to move this way around the circuit, okay? And because the electrons are being pulled from the other side, because this half cell here, because that's where reduction is happening, needs electrons for the reduction of whatever's in there. So that's why, because our standard is that the left oxidation, it's the anode, it's negative. That's why whenever you hook up these two cells, any two cells, other than the standard hydrogen electrode, remember that's always on the left, regardless of what happens. Any other two half cells which you hook up together, the oxidized half cell the cell where oxidation is taking place is always on the left, reduction on the right. So that's why when you calculate E0 or EMF, it's always a positive value. It's always a positive value because of the way we set them up. Okay, even if you calculated it as a negative value, you've got your signs mixed up, but you know, it's just invert it, just make it positive. Okay, so that's what's happening here. Is the electrons are traveling from left to right, you know, being released here and used up here. Okay, so lone you can absolutely rely on when it comes to you know, just checking yourself, like what's happening in each half cell here. Okay, and of course, if this aluminium electrode is being broken down into Al3 plus in solution, the mass of this electrode is going to go down as it gets used up. The aluminium is going to get used up. Okay, whereas if copper is being deposited on the outside of this electrode, the mass of this one is going to go up. Okay, so a bit of logic applied. You can also apply it to changes that we see here as well. Now I need to finish up because I kind of spent an hour, I put an hour aside for this. Last thing I'll say, salt bridge. 2 reasons why the salt bridge is there. One, to connect to complete the circuit, which is always a decent enough answer for like what is the purpose of the salt bridge. But the other thing you've got to remember is that it maintains an electrochemical balance. Okay, I'll write that down. So it maintains an electrochemical balance. Now, this is usually made up of potassium nitrate, okay? A saturated solution of potassium nitrate. Now, just think, as these electrons move from the left-hand half cell, this cell's going to get more and more positive. We're creating 3+ ions, but all the electrons are disappearing. They're going somewhere else, okay? So all the time that this half cell's working, this oxidation side is getting electrochemically more positive because the electrons are leaving, okay, and we're producing obviously positive ions. So what will happen is, oh, I put NO3 plus there, didn't I? The NO3 minus ions will migrate into here to counteract the fact that it's getting more positive. That's what it means when it's maintaining an electrochemical balance. And that's why we use a saturated solution in our salt bridge, because we need as many NO3 minus ions as possible in the potassium nitrate to balance out that change in electrochemistry on the left-hand side. So as it gets more positive, the NO3 minus ions migrate there and just cancel it out and maintain that electrochemical balance. Of course, same is true on the other side. This side gets more and more negative. Okay, because of course we're getting fewer Cu2 plus, okay, we're gaining electrons and they're neutralized. So it gets less positive on this side. So in order to counteract that, you've probably guessed it already, that the K pluses migrate over here to maintain that electrochemical balance. And finally, if we run out of ions in our salt bridge, cell stops working, okay? Because we need to maintain that electrochemical balance. We're getting a current through here. It's a battery after all. We need to generate a current to make the device work. But if our salt bridge runs out here in this sense, then the electrochemical balance can't be maintained and the cell basically just stops. Okay, basically just stops. Okay. So that's electrochemistry. Obviously, I've got videos and worksheets on that, how to calculate E0 cell, conventional representations. This is AQA, so you need to know all about the lithium ion cell and how it works and the equations that go with it, hydrogen fuel cell as well. It's slightly different for each exam board, which I've taken into account. If you're OCR or WJEC, then obviously there's only the things that you need to know in that relevant book, okay? So, any questions? Because basically I've done my hour now, over an hour. So how are we? Any questions about the course? Any questions about Electrochem? Oh, I said I'd give you these Electrochem questions. Let's do that. So these are, again, from all the major exam boards. So you can download those and kind of use those as you see fit. Okay. So thanks again for coming along today, guys. Really, really appreciate it. Thank you for asking your questions. Thank you for getting involved. As I say, if you want any advice, that's all right. My pleasure, Alice. You were very quiet during the electrochemistry there. I was wondering whether I kind of lost you maybe, but yeah, thank you very much. So if you like these live sessions, Chemistry Coach members, I'm going to be coaching you right the way through your exams. So every week we're going to have a coaching session looking at a different aspect of the exams, how to revise, how to analyze papers yourself. So they're not revision sessions per se, even though I will answer your questions if you've got any. What they are is just coaching. How to actually make the most of what you know, how to revise things efficiently, how to attack your exam. So I'll be coaching you from a week on Sunday, right the way through to the end of the exam. So if you fancy a bit of that, like I said, with the discount code down here, it takes 20% off. So if you are AS, then it's 32 quid, just one off, okay? It takes right your way through to July. If you're A level, then it brings it down to 60. And again, that is just one payment and you get access to literally everything, including the AI and my coaching sessions right the way through until the end of the exams. Okay, so yeah, hit me up if you're interested in that. Okay, thank you very much, guys. I will love you and leave you. Tomorrow, what are we doing tomorrow at 1 o'clock? We are looking at NMR, all right, and how to attack NMR questions and the Arrhenius equation as well. So there's always questions on those two things in the exams. I'm going to give you my best tips, tricks, hacks, and advice for those two question types tomorrow at 1 p.m. if you can make it. All right, guys. So I'll catch you later and hopefully see you inside Chemistry Coach. See you later.